Some gemstones are extremely rare. A smaller group is extremely valuable. But a very small number create a different kind of problem. They introduce uncertainty, even among experts. Not uncertainty about beauty, not uncertainty about authenticity, uncertainty about interpretation. Some change appearance depending on environment. Some require advanced laboratory analysis to confirm identity. Some are so rare that reliable comparison becomes difficult. And in certain cases, the challenge is not determining value, but determining certainty. Here are 10 gemstones whose complexity can make verification unusually demanding in 2026. Ranked 10th. Hackmanite, the gemstone that refuses to stay visually consistent. At first glance, hackmanite appears calm, even understated. A soft violet tone, a slightly translucent body, a structure closely related to sodalite, a mineral family not typically associated with controversy. Nothing about its appearance suggests instability. Nothing suggests unpredictability. And yet, hackmanite introduces a quiet problem that most gemstones never have to face. It does not always look the same twice. Hackmanite is known for a rare optical behavior called tenebrescence, a reversible color change triggered by exposure to ultraviolet light. Under UV radiation, the crystal lattice temporarily rearranges the way it interacts with light, often deepening the stone's saturation dramatically. Shades can intensify from pale lavender into richer violet or even purplish pink. Remove the ultraviolet source, and the color can slowly fade back again. This transformation does not damage the gemstone. It does not alter the chemical composition. It does not reduce structural integrity, but it introduces something documentation systems are not designed to accommodate: visual inconsistency. A gemstone photographed under one lighting environment may appear noticeably different when viewed later under another. A catalog record created under neutral conditions may not fully represent the stone's appearance after exposure to sunlight, display lighting, or ultraviolet sources used during examination. Even experienced gemologists may observe variations in saturation depending on environmental history. The stone itself remains stable, but the appearance of the stone does not remain fixed in a single visual state. For collectors, this phenomenon creates fascination. For laboratories, it creates classification notes. For documentation specialists, it introduces a subtle but persistent complication. When visual appearance becomes dependent on environmental exposure, photographic records become less definitive as identification references. Consistency is one of the quiet assumptions behind most gemstone documentation systems. Color, tone, and transparency are expected to remain stable enough to support long-term verification. Hackmanite challenges that expectation. Two images of the same stone, taken under different exposure histories, may not immediately appear identical, even when the material itself has not changed. This does not make hackmanite unreliable, but it does make it unusually sensitive to context. And in a category of gemstones where identification often relies on repeatable visual confirmation, even small variations can introduce hesitation. Not because the gemstone lacks authenticity, but because authenticity becomes slightly harder to demonstrate in a single fixed moment, which is precisely where the concept of risk begins to take shape. Not in the chemistry of the stone, but in the consistency of how it is perceived. And this is only the beginning of how uncertainty can enter the world of rare gemstones. Ranked 9th, Paraiba tourmaline. When color becomes a verification problem, some gemstones are evaluated by what they contain. Paraiba tourmaline is evaluated by how convincingly it contains it. Copper, a trace element rarely found in concentrations strong enough to produce the level of saturation seen in this stone. Yet in Paraiba tourmaline, copper does more than influence color. It defines the identity of the gem in the eyes of the market. The visual impression is unmistakable. Blue that appears charged with internal energy. Green that seems almost electrically amplified. A glow that does not simply reflect light, but appears to project it outward. But the more intense the color becomes, the more the question shifts. What created it? Color in gemstones is often a result of trace elements substituting into the crystal lattice during formation. In most cases, these substitutions are well understood and relatively consistent across deposits. Paraiba tourmaline disrupted that expectation. When copper-bearing material first appeared, its chromatic intensity exceeded what collectors and gemologists were accustomed to seeing in the tourmaline group. Later discoveries expanded the geographic range of similar material, introducing new variations that could visually resemble earlier stones while forming under different geological circumstances. The appearance remained compelling. The interpretation became more layered. Copper presence can be confirmed through advanced analytical methods such as laser ablation, ICP-MS, or spectroscopic testing capable of detecting trace element signatures within the crystal structure. These processes help distinguish copper-bearing tourmaline from visually similar stones whose color results from different chemical pathways. The distinction matters because visual similarity alone cannot reliably determine origin, formation conditions, or treatment history. Some stones exhibit color concentrations influenced by heating processes designed to improve clarity or modify tone. Others display naturally occurring copper signatures, but differ in a saturation due to variations in geological environment. Under standard observation, these differences may appear subtle. Under analytical examination, they become critical, because the defining characteristic of Paraiba tourmaline, its vivid copper-related color, is also the feature most dependent on confirmation. Not confirmation that the stone is beautiful, confirmation that the cause of that beauty is correctly understood. When identity depends not only on what is seen, but on what must be measured at microscopic levels, documentation evolves from descriptive to investigative. Each report becomes part of the stone's narrative. Each analytical result refines how the gemstone is interpreted within the broader classification of tourmaline. The risk does not come from instability. It comes from the precision required to ensure that appearance and composition are aligned. And in a field where subtle differences in trace chemistry can influence how a gemstone is categorized, even strong visual confidence does not eliminate the need for deeper verification. As the ranking continues, the next category of risk moves beyond chemistry, into the physical limitations of the crystal structure itself. Ranked 8th, sphene. When brilliance exceeds structural confidence. Light does not behave quietly inside sphene. Instead of passing cleanly through the crystal, it fractures into spectral flashes that often exceed what observers expect from transparent gemstones. Reds appear beside greens. Yellows intersect with orange fire. In motion, the stone can display a dispersion intensity that rivals, and in some cases surpasses, what is typically associated with diamond. This visual performance immediately attracts attention. Collectors often recognize sphene not by color alone, but by the dynamic way light separates as it exits the stone. Even subtle movement can produce rapid shifts in spectral response, giving the gem an almost restless optical presence. But optical intensity introduces a different type of consideration. Sphene ranks between 5 and 5.5 on the Mohs hardness scale, placing it below many gemstones traditionally used in jewelry intended for regular wear. The crystal structure, while capable of producing exceptional dispersion, is also more susceptible to abrasion when exposed to repeated contact with harder surfaces. The same internal arrangement that allows light to separate so dramatically can also make facet edges more vulnerable over time. This creates a paradox rarely encountered in gemstones known for strong optical performance. The feature that makes the stone visually exceptional does not automatically support long-term durability in everyday environments. In controlled settings, display collections, occasional wear, or protected mountings, sphene performs reliably. Under conditions involving continuous friction, however, the edges of the crystal may gradually soften, affecting how light exits the stone and how the brilliance is perceived. This does not imply instability in composition. The mineral remains chemically sound. The sensitivity exists at the structural level, where repeated mechanical interaction can influence surface precision. For documentation, specialists and collectors evaluating long-term preservation, structural resilience becomes part of the assessment process. Not because the gemstone lacks visual distinction, but because maintaining that distinction requires awareness of environmental exposure. Unlike gemstones whose optical appeal and durability align closely, sphene separates those attributes into two independent considerations. One governs how the stone interacts with light, the other governs how the stone interacts with time. When a gemstone's defining advantage depends on preserving extremely precise facet geometry, even minor wear patterns can influence the intensity of its visual effect. Over extended periods, the difference between exceptional brilliance and reduced dispersion may depend less on rarity and more on how carefully the crystal structure is protected from gradual alteration. As the sequence continues, the next category of complexity shifts away from structural sensitivity toward questions of geographic origin that cannot be replicated once the source is no longer active. Ranked 7th, Kashmir sapphire. When geography becomes part of the gemstone. Few gemstones are evaluated through location as closely as through composition. Kashmir sapphire occupies a category where geographic origin is not simply descriptive. It is foundational to how the stone is understood within the gem trade. The mineral itself belongs to the corundum family, the same crystalline structure that produces sapphires from Sri Lanka, Madagascar, Myanmar, and numerous other deposits around the world. Chemically, these stones share the same fundamental framework, but Kashmir material displays a visual character that specialists often describe as distinctly velvety, a soft diffusion of light caused by microscopic inclusions that scatter illumination in a way that reduces harsh internal reflections. Instead of sharp brilliance, the stone exhibits a refined glow that appears evenly distributed throughout the crystal. This optical texture is subtle, yet recognizable. Attempts to replicate similar appearance through treatment or alternative sources rarely produce the same balance between saturation and diffusion. Even stones with comparable color intensity may display different internal light behavior when examined under magnification or controlled illumination. The historical deposit responsible for these sapphires was active primarily in the late 19th and early 20th centuries in a remote region of the Himalayas. Production was limited, geographically constrained, and ultimately finite. As mining activity diminished, the available supply became fixed within existing collections, auction records, and inherited estates. Because no modern deposit has consistently reproduced the same combination of trace chemistry and inclusion structure, determining geographic origin requires careful examination using microscopic inclusion analysis, spectroscopy, in comparison with reference samples. Documentation may include origin opinions issued by independent laboratories, but these opinions rely on probabilistic assessment rather than absolute geographic proof. Natural geological processes rarely leave signatures that function as precise coordinates. Instead, identification depends on convergence of indicators. Inclusion morphology, trace element, balance, optical behavior under magnification, historical comparables. Even small variations can influence how strongly a stone aligns with known reference material. The sapphire itself remains chemically stable. What varies is the confidence with which its geological history can be reconstructed. When origin becomes inseparable from identity, verification extends beyond confirming species and variety. It requires evaluating whether the observable characteristics align with a geographic environment that is no longer actively producing material. In most gemstones, origin enhances narrative value. In Kashmir sapphire, origin defines interpretive context. As the ranking progresses, the next category of complexity moves away from geographic dependence toward gemstones whose perceived value can shift dramatically based on how lighting conditions influence what the eye observes. Ranked 6th. Alexandrite. When value depends on the conditions of observation, green under daylight, red under incandescent light. Between those two visual states exists one of the most discussed optical transitions in gemology, a phenomenon strong enough to influence how the gemstone is perceived, categorized, and evaluated across different environments. Alexandrite belongs to the chrysoberyl mineral family, yet its reputation is defined less by composition and more by behavior. Chromium within the crystal lattice selectively absorbs portions of the visible spectrum, allowing the stone to respond differently depending on the dominant wavelengths present in surrounding illumination. Under daylight balanced light sources rich in blue and green wavelengths, the stone often appears green to bluish green. Under warmer lighting environments dominated by longer wavelengths, the same crystal can shift toward purplish red or raspberry tones. The material itself remains unchanged. Only the spectral conditions surrounding it differ. This creates an unusual situation in which visual documentation depends heavily on lighting variables that are not always standardized across photographic, retail, or display environments. A gemstone photographed in one lighting context may present a distinctly different identity when viewed in another. Even small variations in color temperature, measured in Kelvin, can influence the balance between transmitted and absorbed wavelengths, subtly affecting the perceived strength of the color transition. Some stones display a dramatic shift that is immediately noticeable. Others exhibit a more gradual change that becomes apparent only when lighting conditions are carefully controlled. Because the strength of the phenomenon can vary significantly between specimens, classification descriptions often include qualitative assessments of transition intensity rather than relying on a single fixed visual state. In documentation contexts where color is expected to function as a stable identifying characteristic, this introduces an additional interpretive layer. Two observers evaluating the same gemstone under different lighting environments may emphasize different aspects of its appearance. Laboratory reports may reference the presence of color change behavior, but the perceived intensity of that change can remain dependent on viewing conditions. The gemstone itself is structurally stable. The variability exists in how light reveals different aspects of the crystal's interaction with the visible spectrum. As a result, visual identity becomes partially conditional, influenced by the spectral composition of illumination rather than by any alteration in the material itself. When classification depends on observing a relationship between two lighting environments rather than a single fixed appearance, verification becomes a comparative process rather than a purely descriptive one. And when observation becomes comparative, context becomes inseparable from interpretation. Further along the ranking, complexity shifts away from lighting-dependent behavior toward gemstones whose rarity introduces challenges not of perception, but of statistical reference. Ranked fifth, grandidierite, when classification exists outside familiar reference points. Commercial gemology functions most efficiently when a material can be compared against an established body of examples. Color ranges are known, optical responses are documented, formation environments are widely studied. Grandidierite resists that convenience. Discovered in southern Madagascar in the early 20th century, this magnesium-aluminum borosilicate mineral remained for decades primarily a museum specimen rather than a faceted gemstone. Transparent material suitable for cutting appeared only in extremely limited quantities, and even then, often in sizes smaller than what collectors typically associate with commercially visible gemstones. The scarcity of faceable material did more than limit availability. It limited familiarity. Because so few transparent specimens entered circulation, grandidierite developed outside the standard pattern through which most gemstones become widely understood. Reference samples remained rare. Comparative datasets remained small. Even experienced observers encountered relatively few opportunities to evaluate the stone in person. The crystal structure exhibits pleochroism, a directional optical effect in which the gemstone displays different colors depending on viewing orientation. Shades can shift between bluish-green, green, and sometimes slightly grayish tones, depending on how light travels through the internal lattice. In well-known gemstones, pleochroic behavior is supported by extensive visual references across many specimens. In grandidierite, each example contributes disproportionately to the collective understanding of the material. Subtle variations in tone or transparency can appear more significant when fewer comparative points exist within the gemological record. Identification itself is not ambiguous. Refractive index, birefringence, and spectroscopic characteristics provide measurable confirmation of the species. The complexity arises from contextual interpretation, understanding how a specific specimen fits within a limited spectrum of known material. When a gemstone is encountered infrequently, each additional verified example becomes part of the framework used to interpret the next. Documentation expands gradually, often shaped by individual discoveries rather than broad statistical sampling. In environments where classification typically benefits from extensive precedent, Limited familiarity introduces a quieter form of uncertainty. Not uncertainty about what the gemstone is, but uncertainty about how representative any single specimen may be within the larger population. As reference frameworks remain narrow, interpretive confidence develops more slowly. And when context evolves incrementally, each new specimen subtly reshapes the boundaries of expectation. Beyond this point in the ranking, the nature of complexity changes again, moving from gemstones defined by limited familiarity to materials whose identity itself was only recognized after being mistaken for something else entirely. Ranked fourth, taaffeite, recognized only after being mistaken for something else. For many years, this gemstone existed in plain sight without being recognized as its own mineral species. Cut, polished, and circulating within collections, taaffeite was originally assumed to be spinel, a far more familiar gemstone sharing similar visual characteristics. Both materials can display soft violet, pinkish, or mauve tones. Both may appear transparent with relatively high brilliance. Under casual observation, the differences are subtle enough that even experienced handlers historically had little reason to question the identification. The distinction emerged only after careful gemological examination revealed optical properties inconsistent with spinel. Spinel is singly refractive. Taaffeite is doubly refractive. That single difference altered the classification entirely. When measured through polarized light testing, the crystal demonstrated birefringence, an optical property indicating that light travels through the structure in two distinct directions, producing measurable separation of rays within the material. This observation confirmed that the stone did not belong to the spinel group at all, but instead represented a separate mineral species previously unrecognized in faceted form. Unlike many gemstones discovered directly in geological environments, taaffeite entered scientific literature through a cut specimen already circulating within the gem trade. Its identity was established only after inconsistencies between expected and observed optical behavior prompted deeper investigation. The chemical structure, containing beryllium, magnesium, and aluminum, differs from spinel despite visual similarities that can make distinction challenging without instrumentation. Because the gemstone was initially encountered as an already cut material, early reference samples were limited in number, and each confirmed specimen contributed significantly to expanding understanding of its physical and optical profile. The rarity of gem-quality material has remained consistent, with relatively few transparent specimens entering the market over time. Each additional confirmed stone requires careful analytical comparison to ensure accurate identification within a narrow dataset. The significance of taaffeite does not arise from visual instability or structural fragility. It arises from historical context, a gemstone that demonstrated how closely appearance can align across different mineral species, and how classification sometimes depends on detecting differences invisible to the unaided eye. Where many gemstones are recognized immediately through familiar characteristics, taaffeite illustrates how recognition itself can arrive gradually, not because the stone was hidden, but because the tools required to distinguish it from visually similar materials were not always applied at the moment it was first observed. Further along the ranking, rarity introduces a different type of challenge. Not the difficulty of distinguishing between similar materials, but the difficulty of evaluating a gemstone for which very few comparable examples exist at all. Ranked third, painite, when rarity reduces the reliability of comparison. In most areas of gemology, confidence grows from repetition. Multiple specimens allow patterns to emerge. Patterns allow boundaries to form. Boundaries allow classification to stabilize. Painite developed under very different circumstances. For a period of time, the number of known crystals could be counted individually, each specimen contributing disproportionately to the global understanding of the species. Early documentation described the mineral as one of the rarest crystalline materials identified in gem-quality form, not because it lacked geological structure, but because the combination of elements required for its formation occurred under extremely constrained conditions. Calcium, zirconium, boron, aluminum, and oxygen combine in a structural arrangement rarely encountered in transparent crystals large enough to facet. The result is a mineral whose presence remained limited across decades of collecting, study, and cataloging. When a gemstone exists in such small numbers, comparison becomes less statistical and more case-based. Each additional verified specimen does not simply confirm expectations. It expands them. Color has been observed ranging from reddish-brown to orangish-red, occasionally displaying internal characteristics that differ subtly between examples. Minor variations in trace chemistry can influence transparency, tone, and how light interacts with the crystal lattice. In gemstones supported by large datasets, variation is expected and easily contextualized. In gemstones with limited population samples, variation can appear more significant simply because fewer reference points exist. Analytical identification of painite is well established through refractive index measurement, birefringence observation, and spectroscopic confirmation of trace element composition. The difficulty does not arise from determining species when proper testing methods are applied. It arises from the limited availability of comparative material through which expectations are formed. Auction records, laboratory archives, and private collections contain relatively few documented examples, meaning each additional specimen contributes to refining the descriptive range associated with the gemstone. Rarity in this context does not only influence visibility in the marketplace, it influences the breadth of shared familiarity among specialists. When reference material remains scarce, interpretation evolves gradually as new observations expand the dataset. Each stone becomes part of the framework used to understand the next. As a result, classification confidence develops through incremental accumulation rather than broad statistical reinforcement. Beyond this point in the ranking, complexity shifts away from limited population size toward formation environments so restrictive that the probability of repetition becomes exceptionally low. Ranked second, red beryl, formed under conditions that rarely occur. Twice. Geological rarity is often described in terms of scarcity. Red beryl introduces a different dimension of limitation, improbability. Within the beryl mineral family, trace elements commonly produce green, emerald, blue aquamarine, or yellow heliodor. These variations emerge through relatively well-understood substitutions within the crystal lattice, influenced by pressure, temperature, and trace element availability during formation. Red beryl requires a far narrower sequence of circumstances. Manganese must be present in a specific oxidation state capable of influencing the way light interacts with the crystal structure. The surrounding geological environment must provide sufficient heat to facilitate crystal growth, while avoiding conditions that would destabilize the developing structure or prevent transparency from forming. At the same time, the host rock must allow enough space for crystal development without introducing impurities that would cloud the material beyond faceting potential. These requirements do not occur frequently in combination. Known gem-quality material has been associated primarily with rhyolitic volcanic environments in limited geographic regions, where volcanic gases, trace chemistry, and cooling timelines intersect within a narrow window of compatibility. Even within suitable geological settings, crystal formation often produces material too small or included to support cutting. Transparent specimens large enough for faceting represent a fraction of an already restricted occurrence. The mineral itself is structurally stable once formed. The rarity arises from how unlikely the formation sequence is to repeat under comparable conditions. Because relatively few deposits have produced gem-quality crystals, opportunities for direct comparison remain limited. Each confirmed specimen contributes additional information regarding trace chemistry, balance, inclusion structure, and color saturation range associated with naturally formed material. Laboratory verification can confirm species identification through refractive index measurement, birefringence characteristics, and spectroscopic analysis of manganese-related absorption features. What remains less predictable is the frequency with which new material enters the known population. When formation depends on a convergence of environmental factors that rarely align, the appearance of additional specimens cannot be assumed within typical exploration timelines. Rarity in this context reflects not only limited discovery, it reflects limited reproducibility within natural geological systems. As the ranking approaches its final position, the nature of complexity shifts once more toward a gemstone whose identification often depends not on confirming what it is, but on methodically eliminating what it is not. In first place, Musgravite, identified only after every alternative has been ruled out. Some gemstones are recognized by what they clearly demonstrate. Musgravite is recognized by what it refuses to confirm too quickly. Belonging to the taaffeite mineral group, Musgravite shares overlapping structural and chemical characteristics with several closely related minerals. Magnesium, aluminum, beryllium, and oxygen combine within a crystallographic framework capable of producing transparent crystals with subtle grayish-green, olive, or occasionally violet tones. At a glance, the material does not announce its identity. Its optical response can resemble other rare minerals within the same structural family. Refractive index values fall within ranges that partially intersect with known taaffeite specimens. External morphology does not always provide immediate separation from visually similar crystals. As a result, identification often progresses through elimination. Each analytical step narrows the field of possibility. Spectroscopic examination evaluates trace element distribution within the crystal lattice. Measurement of birefringence helps distinguish optical behavior consistent with specific mineral groups. Advanced chemical analysis may be required to confirm compositional balances, distinguishing Musgravite from closely related species. No single test alone defines the conclusion. Instead, multiple observations must converge toward the same classification outcome. Because transparent specimens of Musgravite remain exceptionally uncommon, opportunities for repeated comparison are limited. Each confirmed crystal contributes incrementally to the shared reference framework used by laboratories and researchers. Small variations in trace chemistry can influence tone, transparency, and inclusion characteristics, requiring careful contextual evaluation alongside existing documented examples. The gemstone itself remains structurally stable once formed. The complexity lies in distinguishing it from minerals whose observable characteristics partially overlap. In many gemstones, identification confirms belonging. In Musgravite, identification confirms exclusion. The process does not begin with certainty, it moves gradually toward it. When classification depends on narrowing multiple plausible alternatives into a single remaining possibility, verification becomes inherently methodical. Each analytical layer reduces ambiguity. Each confirmed parameter strengthens interpretive confidence. Not because the gemstone changes under examination, but because understanding emerges progressively through comparison with what has already been established. At this level of rarity, the gemstone is no longer evaluated solely as an isolated object. It becomes part of an evolving framework of knowledge shaped by each additional confirmed specimen. Where most gemstones are defined by observable traits, Musgravite is defined by the precision required to distinguish it from everything else it could have been. Some gemstones are difficult to find. Others are difficult to fully understand. As this list shows, complexity in gemology does not always come from rarity alone. It often comes from how much verification is required to confidently define what a stone truly represents. And sometimes, what appears certain at first glance reveals deeper questions under closer examination. In the next video, the focus shifts to gemstones whose classification changed, and how new laboratory insights reshaped how they are understood today. Because in gemology, knowledge does not stand still, it evolves.